A light year sounds like it's measuring time. It isn't. It's a wall of distance so absolute that nothing humans have ever built has come close to climbing over it in a single lifetime. And one of those things is currently the fastest, farthest-reaching object our species has ever launched. We use the phrase constantly, almost carelessly. This star is 2 light years away. But the number sitting underneath that phrase is not something your brain is built to hold, and it's not something our best engineering has ever come close to respecting. By the end of this, you'll understand why our most extreme technological achievements, the fastest, farthest things we've ever made, barely scratch the surface of what that single word, light year, actually demands. Start with what NASA and the Jet Propulsion Laboratory actually track, in real time, right now. Voyager 1, launched in 1977, is the farthest and fastest human-made object ever sent from Earth. It's currently more than 165 astronomical units away, over 24 billion kilometers, moving at roughly 17 kilometers per second relative to the Sun. That's not an estimate or a thought experiment. It's telemetry, still arriving from a machine older than most of the people watching this. JPL's own mission data is the anchor for everything that follows, because every comparison in this video is measured against a real, moving, still transmitting spacecraft, not a hypothetical one. So what is a light year precisely? It's the distance light travels in 1 year, moving at about 300,000 kilometers per second, the fastest anything in the universe is allowed to go. Multiply that speed across a full year, and you land on roughly 9.46 trillion kilometers. Numbers like that stop meaning anything the moment they leave your mouth. Trillion is just a sound by that point, not a quantity. So here's the comparison to actually keep. Earth's circumference is about 40,000 kilometers. 1 light year is the equivalent of circling the entire planet more than 235 million times, back to back, without stopping. Hold on to that image, circling the Earth over and over into the hundreds of millions, because we're going to come back to it before this is over. Here's the part most people skip past entirely. You don't even start that light year journey standing on Earth's surface, ready to go. You start it fighting your way out of a gravity well. To break free of Earth's pull entirely, a spacecraft needs to reach escape velocity, about 11.2 kilometers per second, or roughly 40,000 kilometers per hour. That's step 1, before the trip has even conceptually begun. And it's already faster than any bullet ever fired from any weapon on the planet. But escaping Earth doesn't mean you've escaped the solar system, and this is where most people's mental map runs out. The sun's gravity still holds you, and beyond that, its magnetic bubble, the heliosphere, extends roughly 120 astronomical units outward, pushing back against the pressure of interstellar space itself. Voyager 1 didn't cross that boundary until 2012, 35 years after launch, at full speed the entire time. And even past the heliosphere, you're still not out. Beyond it lies the Oort cloud, a vast shell of icy debris only loosely bound to the sun, thought to stretch much farther still, by some estimates well over a light year in radius. The edge of our solar system, in other words, is not a line you cross. It's a fog that takes generations just to walk through. And this is before anything has actually pointed itself toward another star. This is just the paperwork of leaving the neighborhood. That should settle what leaving home actually costs. It doesn't settle how fast you'd need to go once you were finally out. Voyager 1, cruising at 17 kilometers per second, would need about 17,000 years to cover that distance. And that's our fastest traveling spacecraft in history, a machine that's already been flying for nearly 50 years. Surely something newer beats that. In December 2024, NASA's Parker Solar Probe broke the outright human-made speed record, reaching roughly 192 kilometers per second, about 692,000 kilometers per hour, as it dove through the sun's outer atmosphere. At that pace, it's still around 1,500 years to cross a single light year. Then there's the concept still sitting on the drawing board, not yet built, Breakthrough Starshot, a proposed fleet of gram-scale probes accelerated by ground-based lasers toward roughly 20% of the speed of light. At that velocity, the math is almost elegant, about 5 years to cross a light year, within a human lifetime, even within a single career. But notice the phrase gram-scale. That's a probe smaller than a postage stamp, carrying a camera and a radio and nothing else. Nothing about that design scales up to a spacecraft carrying propellant, shielding, life support, or a human being. But that's not the strangest part of this problem. The strangest part is what happens to anything moving that fast once it's actually out there, alone, in the dark. Speed alone isn't the obstacle. Survivability is. Pushing any meaningful mass to even a fraction of light speed requires energy output that dwarfs anything current propulsion technology can generate. Chemical rockets, ion drives, nuclear thermal designs, none of it gets a crude spacecraft anywhere close to relativistic speed. Then, there's what's physically waiting in the space itself. Outside a planet's protective magnetic field, unshielded spacecraft sit in a constant bath of cosmic radiation. High-energy particles capable of degrading electronics and damaging living tissue over long exposure, with no atmosphere or magnetosphere to absorb the hit. And at high velocity, even a dust grain stops being harmless. A particle a fraction of a millimeter wide, struck at a meaningful fraction of light speed, carries the impact energy of a small explosion. At interstellar speeds, empty space isn't empty. It's a firing range, and every kilometer of the crossing adds another chance to take a hit. And suppose, somehow, you built something that survived all of it, shielded against radiation, armored against dust, moving fast enough to actually make the crossing. You still couldn't talk to it in real time. At just 1 light year of distance, a radio signal takes a full year to arrive, and another full year for any reply to make its way back. 2 years, minimum, per exchange. Anything you send out isn't a mission you monitor. It's a message in a bottle, dropped into an ocean with no shoreline. And here's the part that should genuinely unsettle you. Everything we've just covered, the energy, the radiation, the dust, the silence, is the accumulated cost of crossing one single light year. Just one. So say we solve it. Say some future version of Starshot's tiny probes actually makes the full crossing in 5 years, dust and radiation and all, exactly as designed. You'd expect that to feel like an arrival, like the hard part is finally over. It isn't one. 1 light year doesn't get you to another star system. It doesn't even get you a quarter of the way to the nearest one. Proxima Centauri, our closest stellar neighbor, sits about 4.2 light-years away. 1 light-year covers less than a quarter of that gap. 1 light-year may not even fully clear the sun's own Oort cloud. And measured against the Milky Way, a disk roughly 100,000 light-years across, holding hundreds of billions of stars. 1 light-year isn't a fraction. It's a rounding error.